Hi guys, sorry I can't be with you there today, but we are going to continue with our last lesson of the first semester and going through sampling distributions of a mean. Last class, guys, we talked about the difference between a sampling distribution for a proportion, where we were figuring out the probability that our sample had a proportion of success was at a specific number. And for the sampling distribution for proportions, we said the average for the sample proportion was equal to the population proportion. And we said the standard deviation for the sample proportion was equal to the square root of PQ over N, right? And when we talked about this formula, we talked about the difference between parameters and a statistic. Parameter coming from your population and a statistic coming from your sample. When we're talking about means, the parameter of a mean, or the population mean, that is represented by the symbol mu, okay? This is your population mean. This is what I would expect as the true mean of an entire population. X bar, this is going to be your sample mean, or the mean that came from a sample, so not from the entire population. Okay, so let's take a look at this question to get us started and thinking. A bottling company uses a filling machine to fill plastic bottles with soda. The bottles are labeled to contain 300 milliliters. The soda dispensed by the bottles vary according to a normal distribution with a mean of 296 milliliters and a standard deviation of 2 milliliters. What are the chances in a single bottle contains at least 300 milliliters? So if you notice here again, they're telling you the quantity of soda dispensed into the bottle is approximately normal. So if X is equal to the amount of soda in the bottle, that means that we know that X is also normally distributed with a mean of 296 and a standard deviation of 2. So we're looking at the probability that X is greater than or equal to 300. Again, looking at in a single bottle. Okay, this we can do our norm CDF, and we know our lower bound is 300. Our upper bound is a very large number. Your mean is 296 and your standard deviation is 2. And we can put that into the distribution function into our calculator. So I'm just going to get that for us. Second distribution, norm CDF, 300, very large number, 296 and 2. This probability is 0.0227, okay, or roughly that amount. Now, that is everything that we've already done, right? What are the chances that a single bottle contains at least 300 milliliters? Listen to the wording in the new question. It says, if I were to take a random sample of 100 bottles, now it's asking what is the probability that the average amount in the 100 bottles is at least 300. What is the average amount in the 100 what's the probability that the average amount in the 100 bottles is at least 300? This is completely different because now this is not talking about one bottle. This is talking about the average amount in the 100 bottles altogether, right? Let's look at an applet that's going to illustrate this for us. Okay. This applet right here is a wonderful sampling distribution. Now, these numbers are not going to match what you were just seeing on our page, but let's look at this example here. Notice this population, right, parent population, is approximately normal. It's unimodal, it's symmetric, right? And let's say I want to take a look at the sample mean, right? I want to take a look at the sample mean. And let's say my sample size is 25. And I'm choosing this number for a reason. Let's say my number is 25, right? So here's what's going to happen is, let's say I take a sample of size 25, right? Here comes all the 25 pieces. These are the pieces that come out of the population. Here's my sample. And then from that sample, it's going to find an average, and there's the average for that sample. I'm going to do it again. Here's a second sample. right? So 25 pieces. Here's my distribution of my sample in the black. And then it's going to find an average and drop it down. Again, here's a sample of size 25. Okay. Taking 25 random pieces. It finds an average and drops it down. And take a look at what happens as you do more sample after more sample of size 25 or more, right? You can start to see, right? No more animation, just going over. You can start to see the sampling distribution for the mean start to change. It starts to kind of pop up. I'm going to add in another 10,000 and another 10,000 and another 10,000 samples, right? And what you kind of see here is that the sampling distribution for the mean, I can see that the mean for the population is pretty much the mean for the sampling distribution of the sample mean. This kind of makes sense because if I think that on average, right, the bottles are filled to 296 milliliters, if I take a sample, I would expect the average to be about 296 also. But what you don't see here is the fact that when I'm looking at the distribution of the sample means, this distribution is a lot more consistent, right? It's not as wide. It's super duper narrow. But how does the standard deviation of the original population, right, match the standard deviation of the sampling distribution? And if you notice here, the standard deviation of the original population is 5, and the standard deviation of the sampling distribution, that's actually around 1. And if I continue to add more samples, at some point it's actually going to hit 1. Notice that the sample size was 25. So it's kind of like saying if I had 5, right? If I divided it by the square root of 25, or the square root of your sample size, right? 5 divided by the square root of 25, or 5 divided by 5, that would give us 1. So this is demonstrating to you what's happening. And notice here in the question we were just talking about, the distribution of the amount of the soda, that was approximately normal, right? So if your population is normal, we can also expect that the sampling distribution, okay, of the means is also going to be normal as well. So let's take a look. Let's take some notes. So here, okay, the sampling distribution of a sample mean will be approximately normal. And technically, this is going to work for any sample size n, as long as the population distribution is also approximately normal. And if you don't believe me, we can go back for a second to that distribution, and I can actually start this all again. And I can say, you know what, let's do a sample size of 5, right? Let's do that. And here's the animated, here's 5, right? Takes the sample, drops it down. I add it in, add it in. Again, I'm coming back to this idea that the sampling distribution of the mean is also normal, okay? The means match, and even the standard deviation is the old standard deviation divided by the square root of your sample size. So what if the population is not normal? Just hold on to that idea. We'll come back to it a little later. So the center, right? The center of all possible sample means, or the center for all possible x bars, is equal to the population mean mu. That means that mu of x bar, or the average sample mean, this is going to be equal to mu. Again, this is because the sample mean is can reasonably estimate the population mean because it is an unbiased estimator. Okay, meaning that it's not biased, it's going to be lining up again with your population average. The standard deviation, or the spread of all the sample means, x bar, okay, is going to use this formula here. The standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. And again, this spread is going to follow as long as your population is greater than 10 times your sample size. Remember, this is your 10% condition. This is your 10% condition. Okay, so let's see this kind of put into action here. All right. Example 1 for SAT scores. SAT scores have a mean of 500 and a standard deviation of 100. So that means that mu is 500, sigma is 100. What about the mean of the random samples of 20 students? Now they're telling us that n is equal to 20. College Boards assures us that the SAT results are normal, right? So SAT results are approximately normal. If you want to talk about the sampling distribution of the mean, there are certain conditions we need to check. We're going to need to check that your sample was randomly taken. All this does is this makes sure that your data is unbiased and that your sample matches your population. We also need to check our independence assumption, meaning that we should be checking our 10% condition. And then we have to check, is our data nearly normal? Okay, is it nearly normal? So let's take a look here. Is my data randomly sampled? Yes, a mean of a random sample of 200 students. Yes, it was randomly sampled. Okay, let's check your 10% condition, right? Is 10 times 20, right, which is 200. Is that less than all students who take the SATs? And that is also yes. This means that we know that the samples are independent. Okay, so B and C are actually the same. What I wanted to say was instead of check independence, we're going to check normality. So is the distribution approximately normal? Right, normality, sorry. And that we do know from the stem of the question. The College Board assures us that SAT results are normal. So the SAT results are normal. So therefore, the sampling distribution of X bar is also approximately normal. That would provide you with a mean for your sample means that would be equal to your population means, that's 500. And a standard deviation for your sample means, which would be equal to 100 divided by the square root of 20, which numerically, 100 divided by the square root of 20, this is 22.3606. Okay? Now that we verified that the sampling distribution for the sample mean is approximately normal, let's take a look at these two questions. Notice here I've bolded for you. What is the probability that your sample of students will have a mean SAT score that is less than 450? That means that they're asking you what is the probability that X bar is less than or equal to, or just less than, 450. We know that X bar follows a normal distribution, so this is norm CDF, lower bound of negative 9999, upper bound of 450. The mean is 500, and your standard deviation is 22.3606, following the standard deviation, the sampling distribution for X bar, or for the sample mean. However, be careful about the wording in the second one. It says, what is the probability that a student will have a score that's less than 450? Notice this is not about a sample now. This is about talking about one student. Now, instead of talking about the probability about a sample mean, they're saying, what is the probability of X, or just that one student, being less than 450? This means that we have to go back to the original distribution, right? Or scores should have a mean of 500 and a standard deviation of 100. Here, we're still doing norm CDF because the population was normally distributed. But here, in this scenario, we are using a different mean and a different standard deviation based on the fact that we're only looking at one student, not a random sample of a specific size. These two probabilities, guys, you can throw into your calculator. I'm not going to actually find them for you guys, but you have the calculator syntax to find it out. Okay. Now take a look at the second question here. It says speeds of car on a highway have a mean of 52 miles per hour and a standard deviation of 6 miles per hour. And they're likely to be skewed to the right for very few fast drivers. So if you start going through, right, you do have a random sample, fine. Random sample of 50 cars. Yeah, okay, 10% condition. But how do you check normality, right? This is saying that the population is skewed to the right. So how do I know that this holds if I don't know if it's necessarily normal, right? Well, here's what we're going to do. Let's try the applet one more time. Let's see how this works. Let's say your sample, right, or your population was not normal. Let's say it was skewed, right? And let's say we're going to do a sample size of 5 just so that we can make this move a little faster here. And let's say I animate 5 pieces and it drops down an average, right? So I animate, here's 5 pieces and it drops down an average. Here's 5 pieces, drops down an average, etc., right? And you might say, well, Mrs. Rodriguez, this is, I don't know, looks approximately normal, right? But you can actually see there's a slight skew to it. In fact, let me overemphasize what's going on here. Let's make the sample size equal to 2, right? So here's 2 things, we find an average. My sample size is 2, I find an average, and etc. You can actually clearly see with a small sample size, right, the sampling distribution of the sample mean. This is not normal, right? However, what you did notice is that when we dealt with a sample size of 5, right, it looked like it got closer to being normal. And even more so, let's say if I went to a sample size of 25, I'm getting closer and closer and closer to having a sampling distribution that is normal. So a sampling distribution for the sample mean being normal. So what you're actually witnessing here, what you're actually witnessing happening right now, is this is your central limit theorem. And what the central limit theorem basically states is that it actually, the shape of your population distribution is actually irrelevant. Because if your sample size is large enough, the sampling distribution of the sample mean is going to be approximately normal. And then we can still use the formulas that we were just talking about to calculate these probabilities for the sampling distributions. So what you're seeing here, okay, is what we call the fundamental theorem of statistics, or the central limit theorem. And basically what it's saying is the sampling distribution of any mean, right, no matter if the population is normal or not, is going to become normal as the sample size grows. And all we need is for the observations to be independent, and they have to be collected with randomization. And those were the conditions we were talking about before. Independence, randomization, is your sample size large enough? We don't even care about the shape of the population because as long as your sample size is large enough, the central limit theorem will hold. Basically, the cutoff for the central limit theorem, in terms of like how big does the sample need to be, your n has to be greater than 30, okay? 30 seems to be the consistent cutoff. Some textbooks say 40. I think 30 is a safe bet in terms of the value for your sample size that would apply the CLT to make it work, okay? So the CLT, their central limit theorem, is pretty cool. Not only does it does the histogram of the sample mean get closer to the normal model as the sample size grow, but it's true regardless of the shape of the population distribution, which is actually pretty cool. This is just kind of a summary here to remind you of the fact that we've been dealing with so many formulas for means and for standard deviations the last few days. Just to kind of clarify, like, you can't confuse all of these formulas, right? Binomial and geometric distributions, they had their own means and standard deviations. Remember, binomial dealt with counts. This was n times p. The standard deviation was the square root, was the square root of npq. The geometric distribution had a mean of 1 over p. I forget the standard deviation. I'll fill that back in a second from the reference sheet. But the sampling distribution, for the sample proportions, we said the mu for p hat, this is equal to p, and your standard deviation for p hat, this is the square root of pq over n. And now we have the sampling distribution for sample means. So mu x bar is equal to mu, and sigma x bar is equal to the standard deviation over the square root of n. So be careful that the sampling distributions for means and proportions are not confused with the sampling distribution for the geometric distribution and for the binomial distribution. The biggest thing to remember here, guys, is that your random sampling condition, your independence assumption, and the nearly normal condition. And notice here I mentioned the CLT if you're not normal population, or if your population is just normal itself. Okay, these are the 3 conditions you're going to need to check. So why don't you take a second, pause the video here, and try example 2. Remember, you're checking your simple random sample, your independence, and then your normality. Okay, so let's take a look. Random sampling condition, I'm going to give this a check because it says random sample in the question. Please don't give a check on your homework or on your test. Please write out the question states that it was randomly sampled. Let's check your 10% condition. 10 times 50, right? That is 500. Is there more than 500 cars on the highway? Yes. So there's more than 500 cars on the highway. And essentially what that means is that you have independent samples. So this works for your independence. Then I'm just going to check the normality. But the problem here, right, is they said that my population is actually likely to be skewed to the right. So how will I know if the sampling distribution is normal? Here, guys, since your n is greater than 50, the central limit theorem holds, right, which means that x bar will be approximately normal. Just because my sample size is large enough, right? Since my sample size is 50, which is greater than 30. My apologies, I wrote the wrong number. Since n is greater than 30, the CLT holds, right? So what does that mean about the mean and the standard deviation? That means that mu of x bar is going to be equal to the population mu, that's 52. And the standard deviation for x bar is going to be equal to the standard deviation over the square root of n, or 6 over the square root of 50, which we will grab from the calculator. Sorry. And this is equal to 0.8485. So again, what is the probability that the mean speed of your sample, or what is the probability that x bar is less than or no more than 45? Again, since I know it's approximately normal, this is going to be norm CDF. Your lower bound is going to be negative 99999. 45 is going to be your upper bound. The mean is 52, and the standard deviation is 0.8485. This should be a very small probability. Think about the fact that 45 is 7 away from 52. You're more than 7 standard deviations away from the mean, so this should be a really small probability. It might even be close to 0 when you put it into the calculator. Okay, I highly suggest, guys, trying example 3 if you have time. Otherwise, we have one more formula to go over before you have time left to practice. And that is the sampling distribution for the difference in sample means. This is very similar, guys, to what we talked about just the other day for the difference in the sample proportions, except for the fact instead of dealing with proportions, you're dealing with means. But the ideas behind it are all the same. So it says a potato chip manufacturer buys potatoes from two different suppliers. The weights from potato farm A are approximately normal with a mean of 75. So I'm just going to say mu A, that's 175. And the standard deviation of A, that is equal to 25. And the weights of potatoes from farm B are approximately normal with a mean of 180 and a standard deviation of 30. It says when shipments arrive at the factory, inspectors randomly select a random sample of 30 potatoes from each farm and they weigh them. And they're surprised when the average weight of the potatoes from sample farm A is higher than the average weight of the potatoes from sample farm B, right? So what is the probability that the inspectors would witness such an event? So remember, just like when we checked before, we have to check for the shape, the center, and the spread, right? So the shape, we want to know, is it approximately normal, right? That is what we want to check for. And to check for more normality, make sure that your N1 is greater than 30 and your N2 is greater than 30. If your population is not symmetric and normal, or you can check that both distributions are normal. Again, just because there's two groups. So the shape will be approximately normal if you follow your CLT, or if the population distributions are already normal, then you're good to go. Okay. The center, we would expect that the average, right, for X bar, I'll call it A, minus X bar B, this would be equal to mu sub A minus mu sub B, right? A minus B. Doesn't matter, again, the order, very similar to like what we were talking about the other day in class. But your center should be the difference between the two means. Okay, and this would work again if you check your randomization condition. Was this a random sample? Because we want to make sure that our sample means are close to our population means, or it's a good estimate. Okay, now the spread, that's your standard deviation, again for X bar A minus X bar B. Again, combining the variances. So this one gets a little tricky because it was the standard deviation of X bar A, right, squared now over the sample size, right, of A. And this is going to be plus the standard deviation for X bar B. That whole thing gets squared all over the sample size for group B. Well, it's not X bar, sorry. I'm going to take this subscript of X bars off. It's just of A and of B, okay? And again, you can check and use this standard deviation as long as the 10% condition holds. All right, so again, you have to check your 10% condition for both groups. All right, so let's take a look here. Big picture saying, what is the probability that the mean weight from farm A exceeds the mean weight from farm B? So check your conditions. Both sample sizes are 30, meaning that my central limit theorem is going to hold for both. So that would work in terms of normality. Both of the potatoes are randomly selected. That would mean I have a random sample. And also, if we do 10 times 30, which is 300, there's definitely more than 300 potatoes from both farms being sent. So we know this distribution will hold. So let's do the actual work. So we have mu of X bar A minus X bar B, right? What do we expect as the average difference between the two? That's 175 minus 80. Sorry, minus 180, which is negative 5. And we have the standard deviation of X bar A minus X bar B. This is the square root of 25 squared over 30 plus 30 squared over 30, all in a square root. So let's get a value for that. Plus, and this is 7.1297. Okay, so we're looking for the probability, right, that A minus B, or x bar A minus x bar B, x bar A minus x bar B, right? So the difference between the two average. Now, if I want A to be greater than, right, to exceed the weight of B, that would mean that A minus B has to be greater than 0, right? It's almost like you can start with A greater than B and then subtract the B over. So I need this difference to be greater than 0, which means, let me make this a little smaller, okay? We can now use norm CDF because we verified that the distribution works. Lower bound of 0, upper bound of positive 9999, the mean of -5, and a standard deviation of 7.1297. You can plug that in your calculator and get a probability from there also, okay? But the big takeaway from today, all right, taking a look at this, is the sampling distribution of a sample mean. You should be comfortable with looking at the sampling distribution for one sample mean, right, for one mean from one sample, or even looking at the difference between the means for two separate samples. All of the formulas, guys, that we've been discussing, one more time, these are all available for you on the reference sheet. Again, if you go to the reference sheet, which you will get this on your exam, but it's always good if you know them by heart, you can see here population for one proportion, for two proportions. Don't worry about standard errors. We're not talking about those yet. That's not until January. But notice, again, parameters of the sampling distributions. All the formulas are there. And if you scroll down, you actually also see the formulas for the means, right? Random variable for one population or for two populations. And you can see that again right there on the reference sheet. Again, do not worry about standard errors. We are not ready for that yet. All right, so please be aware. But you have all the formulas right there for you in addition to the binomial and the geometric distributions, okay? I would highly suggest trying another one of these examples. You're also going to have a homework assignment, so you could practice some of those questions there. All right, but I'll go over some of this stuff with you on your review day on Monday to make sure you feel good. But definitely watch as many videos as you can. Use AI to help you kind of get through some of the things that you might still have questions on. But we'll go through some of it before your test. All right. I hope this was helpful and put you guys in a decent spot, at least for my return. Have a great weekend, guys. And also, you can also start working on any of your lab assignments that also have been posted as well. Take care.